Hi, welcome to the Calculus 3 lecture series. And we are in the unit Vectors and the Geometry of Space. This video going to be our last video on this unit. So this video basically is a pretty simple video and a short video. We basically just want to take a look at the different surfaces and very special surfaces in the R3. So we're going to look at the cylinder and quadratic surfaces here. Okay, so now let's first take a look at what is the cylinders here. So let's go back to our worksheets here. All right, so the first things here, let's take a look at our cylinders here, right? So for the cylinders here, so let's say it's a surface composed of the all the line, they are parallel to a given line and passing through a given curves here. So it's not quite the same kind of the cylinder we talk about. Is like a round tube, like a Coke cans, those things, right? So like in here, if you take a look, okay, so if you take a look at this parabolic cylinder, so if you just look at the xy, so x squared equal to the 4ay, so it's a parabola, right? In the xy, remember in the first video, we say in the R3, if any variable is missing from the equation, that means the graph of will be what? Will be parallel to that variables, right? So this is what we call is the trace. So this is what we say is the trace here, right? So basically, if you just look at x and y, and then so without the z, so it's a paraboloid on the, the xy planes here, right? So that's why this is, this is a cylinder. It's kind of like a little weird, right? It's not like the typical round tube, but that's why we generalize it. Okay, so the other ones here, if you take a look at this, we call the elliptic cylinder. So elliptic cylinder, so it's the same thing. You have x squared over a squared plus y squared over b squared. If you just look at this equation in the R2, what is this one? It's ellipse. And then we are missing the z variable, right? So that's why, this one is parallel to the z-axis here. So the same here, like if you only look at this on the xy, so it's x squared over a squared and minus y squared over b squared equal to 1. We call it this is a hyperbola, right? So that's why it's a hyperbola, but it's missing the z. So this is another cylinder. So this cylinder kind of like you cut the Coke can to a half. So this is our traces, right? So this is our traces here. Okay, so we call this is a hyperbolic cylinders here. Okay, so now let's take a look. Okay, so based on these ones here, let's take a look our examples here. Okay, so the first ones here we said so they ask us, they say, hey, true or false, right? True or false. If one of the xy things is missing from the equation of the surface, then the surface is a cylinder. Then we say this is what? This is a true statement, right? That's what is our definition. That means because if that variable is missing from the video number 1, so we know whatever the surface, right, is going to parallel to that, that variable, that axis, right? So if y is missing, then we know it's going to parallel to the y-axis here. Okay, so now the next ones here, we say that identify. So here, the first one, this is x squared minus 5z squares, right? So then you go back to here. So we say, okay, so x squared minus 5z squared. So what is we have here? So we know this is, if I only use the, look at the trace, right? So if I only use the, now I'm only on the xz planes, right? If I only use the trace, this is a hyperbolic, right? So we say this is a hyperbolic cylinders, right? So this will be the hyperbolic cylinders. And because the y is missing, so what do we say? This cylinder going to go along the what? Along the y-axis here, right? So this is a, because if you look at the trace, this is a hyperbole, right? So that's why we call this is a hyperbolic cylinder. Okay, so now let's take a look here, right? So the part B is here by using this graph. So what is this one? So the first one you see here, okay, if I only look at the trace, this trace is a paraboloid, right? So because this trace is a paraboloid, so I know this is the, parabolic cylinder. And so which, like because in here, right? So is along the what axis here? So this is go along the x-axis here, right? So that means when you write it out, you're only going to have y and z's here, right? So because the x variable is missing, that's why it's go along the x-axis here. And then the next ones here, they say, okay, scratch the graph here. So this is x plus 2y equal to 6. Okay, so we say this one's here, let's do the trace here, right? So for the trace here, remember trace is like if I only look at xy planes, right? So, okay, so here, x equal to 0, y equal to what? Y equal to 3, right? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so that's why we say we look at the trace first. When x equal to 0, y equal to 3. When y equal to 0, x equal to what? X equal to 6, right? So this is 6 and 3. So the trace is a lines, right? The trace is a line because I'm missing what? I'm missing the z. So I know this will be what? This will be some like the planes here, right? So it's kind of like the plane. So in here, go to like a, that means it's continuum, right? So this will be the plane. And in fact, this is a special cylinder also, if you kind of, so this is plane because, but it's satisfied the cylinder definitions here. Okay, so now let's take a look here. The second one's here, right? So the second one's here, they said is x squared over 9 plus z squared over 25 here. So think about it. If you only look at the trace, what the trace this is? This is ellipse, correct? Okay, so the ellipse, so let's do, because, so let's take a look, what type of the ellipse this is, right? So because that means it's x and z here, right? So it's x and z. So x over 9 and z squared over 25. So it's 3 and 5, right? So what I'm going to have here, so I'm going to have ellipse something like here. Let's so make sure, okay, so to try to do the 3D is kind of difficult. So let's do like this. Let's extend it that, all right? Okay, so the ellipse here, so because it's z and x, right? So that means in here, the z going to have 5 units here. So here is something like this. Okay, so here. Okay, so here is the, this is elliptical cylinders, right? Because it's missing y, so that's why this graph is go along to the y-axis here. Okay, so basically this is, we call it the cylinder. Then the next things here we're going to talk about is the what? Is the the quadratic surfaces here. So for the quadratic surface, we have 6 very common quadratic surfaces. And then we have we call it ellipsoid, hyperboloid, and hyperboloid of 2 sheets. So basically the key things here when you look here, right? So you still look the traces here. So like if you let the one of the variable become to 0, then you see where is the trace. And also the other things here you might want to pay attention is like how is this graph looks like, right? So like in here, for example, this is the hyperbolic. So here the z is the one with negative signs, right? So that's why the graph is go with the z, it's a parallel z. So for the two sheets is here, so it's go with the z's here, and then the z here is have a positive sign. So that's why it's go with the z. So the next one is here, this is elliptic cone, the elliptic cone. So for the elliptic cone, so you take a look also because here, this is z squares, right? So that's why the z-axis is here. So now for the elliptic paraboloid, so what happens here? So it's z's here, so that's why it is to the z-axis here. So the hyperbolic paraboloid here, that's why it's here, right? That's the how you know, the orientation of the graphs here. Okay, so let's take a look at some of the example. So basically, you know, you just look back to the graph and the equation to see what type of the, you know, what type of the graph it is, right? Okay, so let's take a look at these ones here. So here, this is x squared minus y squared minus z squared equal to 1. So you go back to search for which one have like the 2 negative and 1 positive. So which one you have? Oh, here I have a 2 negative and the positive, right? So this is, we know, so this graph will be the hyperbolic with 2 sheets, right? Okay, so here, that's what we say. This one's here, we say this is, so this is a hyperbolic, and it's with 2 sheets, right? So with 2 sheets. Hyperbolic with 2 sheets. Okay, now, so which one is the positive one? It's x squared, right? So that means that, you know, we're going to parallel to which one? With the axis parallel to is what? To the what? X-axis, right? So if you just compare what is in here, right? Because, you know, this is z is positive, so parallel to the z-axis. So for our example, you know, the x is positive, right? Okay, so now let's take a look. You know, y squared equal to the, you know, so this is y minus 4x squared and 16z squared. So let's take a look which one has y, you know, have 1 and 2 squares, right? Okay, so let's take a look at 2 square, y and 2 squares. Oh, so it's here, right? So it is elliptic paraboloids, right? So that's why is, so you just match what the formula. So these ones here, we know this is elliptic paraboloid. Okay, so because of here, the y is the one without the squares, right? So based on compared to the formulas here, so with the axis parallel to, which axis parallel to? So parallel to what? Parallel to y-axis here, right? So it's pretty straightforward. Okay, so now the part C here is a square, 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 right? So you take a look at square, square, square. And which one is a square, square, square? Okay. Oh, here, so is elliptic cone, right? So I know, okay, so this one here is elliptic cone. And which axis parallel to? Because y is in here, right? So the parallel to what axis? Parallel to y-axis here. Okay, so now for the D, they say, hey, what is this one here? So the first thing here, I say, okay, I need to change it to some quadratic form, right? So like we did it before. So what do we need to do? We need to complete the square, okay? Okay, so let's see here. So this is x squared minus ax plus 16 minus, this is y squared plus 2y plus 1 and plus z squared. And so this one's here is, okay, so this is negative 15. And so I add 16. I need to add 16 here. And so this is a minus 1. So I need a minus 1 here. All right. So now I have, okay, so what I have here, so I have zeros here. So this one's here, this is x minus 4 to the square, right? So x equal to 4 to the square is equal to y plus 1 to the square. And what? Y plus 1 to the square. So hold on, this, okay, so here, no. Okay, so I need to do this way. Okay, so here, my eraser here, okay? Okay, so here, okay, let's be careful here. So this is x squared, so plus z squared equal to y plus 1 to the square, all right? So now we have the y square and the plus and the 2 square. So what is this one's here? Oh, this one's here. This is elliptic. Okay, so this is the elliptic cone again. Okay, so back to here, let's take a look at elliptic cone. So if you don't minus anything, so what happens here? So the center is here, right? So now, because I do have like x minus 4, z, and y plus 1, so if this is elliptic cone, let me go right in here. So here the center at what? So the center at 4, negative 1, and 0s, right? And because of the y is by itself, so that means also I know this is parallel to what? Parallel to y-axis here, okay? Let's take a look at E. Oh, this graph is here. Let's match which one is here. Oh, so here is, right, is hyperbolic with 1 sheet. All right, so this one's here, we say this one is easier. So we say this is a hyperbolic. One sheet, right? 1 sheet. And parallel to what? Parallel to y-axis, right? Okay, so this one's here. So this is what, if you compare to the previous, this is the hyperbolic paraboloid, right? So this is the hyperbolic paraboloid. And what is the parallel to? Parallel to z-axis, right? Okay. So if you compare the graph, so this one's here. So we say, hey, this is hyperbolic, right? So compared to here, you'll see this is a hyperbolic, right? So it's a hyperbolic with 2 sheets, right? So this is a hyperbolic with 2 sheets. And parallel to which one? Parallel to the x-axis. Okay, so if you want to write the equation, you can just go back to the graph and so recognize, that's why I say in the graph here, the most important part is which axis is parallel to, right? So that's why you highlight here like the z here, right? So it's by itself, and then like in here, the same way is here, right? So if you want to have a hyperbolic 1 sheet, and if it, you know, it's parallel to the z, then that's why your z is here. So like the one we did the part E, right? So the one we did the part E, you want to, so this is part E, we say is a hyperbolic parallel to the y-axis. So what you do here, you say x squared a squared plus z squared c squared, and then minus y squared b squared equal to 1, right? So let's just you change the parameter. So that's why I said which axis is parallel to is very important, right? Okay, so that's it. And I don't think you need to remember all those formulas. Those are just for the references. So just show you some pretty neat quadratic surfaces and some cylinders in the R3s here, right? So the only way you need to kind of pay attention is like how the equations was written, and then how the graph looks like. So which axis is parallel to, then you know how to rewrite a new equation if they rotate the graphs here. All right, that's it. Okay, so like I said, this video for this section is very easy video. So basically just give you some introductions about the, what is the R3 surface look like. All right, and this video complete this unit about the vector and the geometry of spaces here. Okay, so our next topic, next unit, we're going to start, we call this the partial derivatives. So we're going to take a look, how do we do the derivative if we are going to the R3 or R4 space right now. Okay, that's it. And you have a good day, and nice to talk to you. And so looking forward to work on the next unit together. Okay, bye.